Hello, I'm John Nightingale, a director at JCT and the Symposium host. Now, the 25th JCT Traffic Signal Symposium was an online event this year, and I'm delighted to bring you a recording of one of the presentations. Now, these recordings would not have been possible without the support of a select group of our event partners. So our thanks go to the Institute of Highway Engineers, ITS UK, keepadistance.co.uk, Siemens Mobility, TWM, and of course, our media partner, Highways News. Please check out their short videos, which will tell you about some of the products and services that they can provide. Now, I hope you enjoy this presentation, and we would love to see you in person for our 25th anniversary event in Nottingham Trent University in September 2021. Hope you enjoy it. Thanks.
Well, good afternoon, delegates. Paul's introduced me. My section of this presentation is a quick intro to our radar products. And my colleagues are going to talk in more detail about the installation on the A27 Ashcombe roundabout near Lewes in East Sussex. My company, Smart Video and Sensing, represents Smartmicro from Germany here in the UK. Smartmicro are probably the global leading manufacturer of passive antenna radars. It's a bit of a mouthful. Their products are used in automotive, aeronautic and traffic management sensors. And if you drive a vehicle from the Volkswagen Audi group, you've probably got a Smartmicro radar built into your car, especially if you've got anti-collision or something like that in your vehicle. We have two main radar types. There's a larger antenna radar, which is designed for interurban routes, covers up to 10 lanes. And the radar we're going to be talking about today is our smaller urban radar, which covers up to 6 lanes and is used primarily for intersection and, as I said, urban routes. And today we'll discuss the UMRR-11 model, which is a 4D and high definition plus radar in a loop replacement configuration in a MOVA application, as I said, at the Ashcombe roundabout. Next slide, please, Shane. Okay, that's the radar. I won't read all of the points on there for you, but I will say that the main points of the radar is it's an intelligent radar. It's very small in size, very lightweight. It draws less than 5 watts, and it's got an extremely high amount of information that comes out of it. So really, the radar is capable of classification, counting, measuring queue lengths, speed, gap, and headway. So using it in the application that we're using it in for loop emulation is only really a very, very small part of its overall capability. We've also recently developed a data logging device, which we're calling Datos X, which can be an after-sales fit for multiple radars at one intersection, and can store data at site, the data that I've mentioned, and send it back to a back office software package. So if anybody's interested in that, please let me know after or please email me after the show. Next slide, please, Shane. Okay, our radar is front or rear firing, and you'll see on the left-hand side there, the diagram shows you the difference between the side fire radar and our front and rear fire radar. The biggest advantage is it overcomes a lot of the occlusion issues that you might get with side fire. Also, the chart on the right-hand side there shows the comparison between our radar and loops in various conditions. They've tested it in thick snow in Finland. They've tested it in heavy rain out in the Middle East, out in the Far East, and they've tested it in very high temperature conditions in the Middle East, and it's performed very well. No one would ever claim that their detector is perfect in all weather conditions, but this radar has certainly been through some extremes. We recently tested in Portsmouth, and the client told us we had a 98.9% comparative rate with the loops on a dual carriageway going into Portsmouth, and then they said, well, perhaps our radar was actually more efficient more efficient than their loops, because they were getting double counting on some of their loops. Next slide, please. The radar is configured using a free traffic management configuration, or TMC configurator tool. It's quite an intuitive tool. You can drag and drop a Google map into the center of it, turn that map into a satellite image if you want, and then you get the second display comes up there and guides you through via a wizard on the setup of or the configuration of the product. It will also tell you whether there's any potential issues that may affect the radar. You can move the position of the radar to get the best or the optimized use of the radar itself. So there's a number of unique features there. Then you can download the software to the radar prior to taking it on site, and then just simply adjust it when you get it to the actual site itself. I'm now going to hand over to my colleagues to discuss the A27 Ashcombe Roundabout mover installation, starting with Andy Reynolds from A1 Plus. Thank you.
My name is Andrew Reynolds. I'm the technology lead for A1 Plus. A1 Plus is the maintenance service provider for Highways England's current Area 4 ASC. This presentation will look at the work done in Area 4 as part of the Traffic Signal Optimisation and Validation Project, which is an annual programme that began in 2017. This is a collaboration between Highways England, A1 Plus, Four-Way Consulting, Talent and SVS. This involves validating and optimising primary and fallback control strategies of traffic signal sites in Area 4. Next slide, please, Shane. Highways England's Area 4 covers Kent, Sussex, and parts of both Surrey and Hampshire. There is a number of strategic routes within the area, also key stakeholders such as Port of Dover and Gatwick Airport. Myself, Talent and Four-Way Consulting have been overseeing the Area 4 optimisation programme from the beginning of the project. Next slide, please, Shane. So the Ashcombe Roundabout is on the A27 between Falmer and Lewes in East Sussex. The road surface was of a very poor standard, and trying to get the area resurfaced was proving too hard and too expensive. So we had to think outside the box for a solution, and it was SVS who told us of the Smartmicro UMRR-11 forward-facing Doppler radar unit. We like this idea as we have seen the masking effects from side-firing radar units on the wider network. So we thought it was a good call to install the first Smartmicro UMRR-11 unit in the UK at Ashcombe Roundabout as a live trial. Now, there were a few teething problems, but these were resolved very quickly. And since the initial visits, we haven't had any issues whatsoever, which equates to around about a 98% success rate for the unit. This was the initial trial to see if this could be used on the wider network as a possible replacement for induction loops. Next slide, please. So as we know, installing inductive loops is a very invasive procedure and can damage a good road surface if done badly. So if we could find an above ground detector that didn't fall over, was able to act as a virtual loop for a low cost, why would we not explore this possibility? All too often, there are emergent resurfacing schemes where more often than not, the loops are forgotten or accidentally damaged, meaning more money to put them right. However, if there was a surface that was loop free, there is yet another cost we could potentially save, as well as the time too. Now, we realise that this would take a lot of conversations before becoming a reality. However, a live test to prove the capabilities of this equipment is definitely a good step in the right direction. I'll now hand you over to my colleague Shane Collins from Four-Way Consulting, who will discuss things in finer detail. Thank you for your time and patience.
Thank you, Andy. So I'm going to look at our findings to date from trialling the UMRR-11. I will talk a bit about the design, installation and performance of the detector. The idea of trialling the radar came about due to the detector issues on the A27 eastbound approach. The approach had a number of faulty detectors, namely AX3, AX4, AX5 and ASL6. MOVA was operational at the site, but we were losing detectors and all lanes were running off either alternate upstream or downstream detection to the X detector. Initially, detectors AX3 and AX4 were set up as a combination detector, and the failure to the detection had a significant impact on performance. The plan was to replace the loop detection shown in the blue box here on the slide with the radar, essentially all phase A, X and in detection. Stop line detection stayed as loops. Whilst the in detectors were working and could have been left operational, we wanted to fully test MOVA operation on each link using the radar. The controller was set up such that the existing loop detection was retained in the configuration as fallback in case anything went horribly wrong. New inputs were included for the radar detection. CFF switches were configured, allowing detection to be switched between loops or radar remotely via the handset terminal, again in case anything went wrong. The detector was commissioned and left operational on the 16th of January 2020. This slide shows the detector installation. The detector is mounted at 6 meters above ground on the offside primary signal pole. You can just see it there, and we've got a zoomed in image of the detector here. It required a dedicated 24-volt DC power supply unit mounted in the controller, and also a relay output junction box to interface with the controller I/O. A wireless connection has also been developed allowing users to connect to the detector via the detector configuration tool and amend detection zones, etc. as required. You can also see the live vehicle detects on the configuration tool, which is useful when commissioning. This is the UMRR-11 configuration tool, and it shows the detection points. You can see the X detectors here and the in detectors here. The radar has a range of up to 300 meters and the field of view covers up to 6 lanes. The virtual detection zones allow the detector locations to be set up in more optimal locations at the site than the existing loop locations. The X detectors were located at 45 meters from the stop line and the in detectors at 90 meters from the stop line. Each detection zone was set up as a 2-meter detection zone. Since going live, we have had a few small teething problems which were resolved easily with a firmware update. The detector has run reliably since this update. COVID has impacted the trial, and to date we have been unable to obtain statistical data comparing the operation of the UMRR-11 against the loop detection. However, we wanted to test the radar worked first before undertaking any statistical analysis, so we undertook visual observations to determine the following. 1, was the detector detecting traffic appropriately? And 2, was MOVA making the correct end of stage decisions? The next 2 slides show videos and screen recordings of the MOVA operation. The first slide looks at the detectors toggling on the MOVA commissioning screen, and the second slide looks at MOVA making its end of stage decision. So hopefully you can all see this. The image on the left shows the approximate location of the detection zones in relation to the video in the center here. Both the video and the screen recording were taken at the same time, and you should hopefully be able to see the detectors toggling as vehicles go over the detection zone. All vehicles were detected, including motorcycles. Very occasionally, the detector would fail to see gaps in traffic in the same lane. With the detector being forward firing and slightly offset from the carriageway, occlusion is minimised, and whilst on site, we never really saw occlusion as an issue. On some occasions, the detector picked up a vehicle but did fail to register a PD. This is being looked into by SVS, and a simple programming fix is anticipated. On this slide, we have a screen recording of the MOVA messages screen, and we have a video taken at the same time of the screen recording of traffic exiting the entry arm. For those of you that know the MOVA messages screen, MOVA ends saturation on link 2 lane 2, which is the middle lane here, on 44 seconds, and it ends saturation on link 3 lane 3 here on 58 seconds. It then optimizes and ends the stage after 59 seconds. The benefits of the detector when compared to loops are that it negates the need for lane closures in the event of detector failure. Slot cutting isn't required, so carriageway surface isn't damaged, and the detector locations can be tweaked if required rather than their locations being fixed. So we should hopefully now see MOVA making its end of stage decision just as the truck crosses the stop line. So in conclusion then, the detector worked with MOVA and MOVA controlled green better than the previous loop operation. Admittedly, there were a few loop detector faults on the arm. The ability to tweak the detector locations and zones was very useful, and it allowed the performance to be optimized. The detector provides the benefits associated with above ground detection mentioned earlier, such as no lane closures, a longer carriageway surface life, and the detector locations can be tweaked. Occlusion was not noticed as being a problem, and the detector picked up motorcycles. There were a few gremlins which were resolved, and the detector has worked reliably since. There are a few things to consider. If there is a detector failure, all detection zones are lost. Smartmicro say the detector has a less than 2% failure rate, but if it does fail, the detector is fairly easy to replace, and you could also consider installing a backup detector. The detector sometimes didn't register PD. However, SVS are looking into this, but a quick fix is anticipated. And the detector sometimes didn't see gaps between vehicles. This wasn't very often and didn't impact movers' end of stage decision. And we also still need to carry out statistical analysis to compare the radar against the loop detection. And thank you for listening, and any questions?